let us continue. So the subject, maybe it's better to keep it in mind here, is this equation which describe the flow in a porous media for the cell density. All this is depending on the parameter gamma, which represents the stiffness of the pressure. And the pressure, for example, is n to the power gamma. And we are interested in the limit gamma tends to infinity. So an instrumental relation which is useful to study that is the equation on the pressure, which is minus p gamma Laplace p gamma minus grad p squared equal p gamma g of p gamma. And in fact, there are parameters, and the parameters which are important are a gamma here and a gamma here. So when gamma is very large, so that's what we proved yesterday by just using some very rough estimates. What we proved yesterday is we can argue that gamma is zero and get, gamma is infinity, sorry, so the other terms are negligible. And this relation holds in the weak sense, which means that it's only by integration by part that you give a meaning to this product. As we will see later, this product doesn't make sense because this is a measure, a singular measure. There is a direct mass on the surface, an hypersurface, and P is not smooth enough. The best we can do is this kind of limit, a strong limit of the gradient in L2. And this is a general method because it uses very weak information, basically what the equation gives you by integration by part. So what I would like to do now is to show there are many other estimates you can get so that the result can be much stronger, but you have to pay with initial conditions which are very stronger. So one of them is the estimate that Marcus was mentioning here. For example, you can estimate quite easily the negative part of the pressure. What you can prove, an estimate, is that the integral of the negative part of the time derivative of the pressure, and this is an integration in x, so this is in the full space, let's speak of the full space. This is controlled by a constant c, which depends on time. So you can say that the compactness in time of the pressure, you can get it, but assuming it initially. So you have to assume at t equals 0. So, of course, the derivative of the pressure is not defined at 0. What you know is the initial data. So you have to assume that the right-hand side has the correct sign. Or it means the negative part of the, if you put everything on the right-hand side, all the negative part of this equation is controlled, which is an assumption of the second derivative. So it's a very quite strong assumption, but if you are ready to do it, you know that the pressure is is controlled. So when you control that, because the pressure is bounded, you control the BV bound, the total variation of the pressure for all times, which gives you compactness because you also control the second derivative in x. But you have to pay it. You have to pay it, and the way it works is quite simple. You use this equation and you differentiate in time. So let's call Z, let's define Z equal dTp, gamma. And if you differentiate that in time, you will get dTz for the first term, minus gamma z Laplace p, minus gamma p Laplace z. And the second term will give you minus 2 grad p grad z equal. And this is, let me call it dTp, so z. And it is important to keep what is the derivative. So you have a g minus, so I differentiate this one, and that I have a plus pg prime. Okay, so now you can put the negative part. So let me recall that the negative part is a positive number, which for some reason is a tradition. So z minus is the maximum of 0 and minus z. So if you take the negative part here, you get exactly the same equation, dt z minus, minus gamma z minus, Laplace p, plus gamma p Laplace z minus, minus 2 grad p grad z minus. And the only thing you pay by Kato inequality is that when you include this convex function here, you get a negative sign. So you get an inequality here, and all the other terms are equality. So this is the equation on that. And now you integrate to compute the total mass of the total integral of z minus. And when you integrate, so what you discover is that these two terms, why is it a plus now? It's a minus, like the others. There's no reason that you change it to plus. When you integrate by part, you get a Laplace p, so you get the term, exactly the same term. So here you will get minus 2 gamma integral of z minus Laplace p. And if you do the same here, you integrate by part, you get plus Laplace, plus 2 Laplace p z minus. So here you will get minus 1. And this is less than gamma z minus 1, g plus p g prime. And the idea is that this, you can put a plus, you can put a minus, you can put a gamma here and a gamma here. And this term, you can get it from the equation again. You find it here. So this term minus Laplace p, this one is minus dTp from the equation, plus grad p gamma squared, plus gamma p g of p. you have to divide by P. Which is better. And so you discover that all this is fine, because now Z is dTp is negative. So this minus term is a positive term. So this one is positive. This one is positive. And this one, you add up to this one. It's a Z minus gamma, which is here, and gamma minus over gamma, which is here. And so what you discover is that when you put it on the right-hand side, you will get minus 2 when gamma is large. So we can forget that if gamma is small, this is small, gamma is large. So there is an assumption that gamma is large enough. This is close to 2. So when he comes here, it will give you a minus 1. So the effect of this is basically to give a minus 1 here. It's not exactly true. There is a number which has to be calculated, but it's basically it's like a minus 1. And so this is G, we say that it's positive, so this is negative, and G prime is negative. So this is negative. Okay? It's not exactly true. I agree that there is a small number but basically this is true. And this means that this quantity is decreasing, which means that you get a control like that. So just by manipulating. So this is an example of estimate you can do, which is quite useful, because then you get compactness of P for the price of this initial data. There are other funny estimates you can do. Then you can also compute estimates on, you can compute the energy in some sense. This is the velocity. So the kinetic energy is basically the grad P squared. So you can also compute the energy, and maybe I will not do it, but if you compute, if you work on that, this is not that. This is finished. If you compute the energy, so I will not do it because it's again integration by parts. You have another estimate which I call energy, which is again an approximation. If you want to put energy, there should be a density, so it should be n grad p. But an example of inequality, where you have several of them like that, is that the integral of grad p squared over 2 plus integral so always in the full space, but as we said, it's if we want, we can keep compact support. If you can get an estimate like there is a constant p, the second derivative of p squared is controlled. So this is what you get if now you multiply this equation by Laplace p. But you can also multiply by p Laplace p and p power gamma Laplace, or p power alpha Laplace p, and find other estimates. So, which means that you can control also higher order quantities, like the second derivative in space-time. Again, if you assume that initially you can do it. So, which means that initially you need that the gradient P is bounded in L2. Which was not used before. Before it was grad P in L2 space-time. Not, and here we have to use that it is L2 in space for all times. It's a little bit stronger. So if you do that, you can get an estimate like that. And there is a nice consequence, which is a general functional inequality. Which I don't know if you have already seen it. It's we discovered it with Noémie David working when we needed some higher estimates on the grad P. And this has nothing to do with anything else. It's just a functional inequalities, which says, and so what I'll give you is a version which is equivalent by Bresch and Al-Azhar, which has the advantage to be completely clean. And it tells you that the integral of a function u power 1/2, 4, is less, I think the number is 16/9, integral of Laplace u squared. Okay, and this is true for any function, let's say smooth with second derivative bounded. Okay, so this is this inequality. So let me count if I'm not wrong. Here you have a 4 times u power 4 times 1/2. You have a u squared. Here you have a u squared. Here you have 4 derivatives, and here you have 4 derivatives in space. So this is homogeneous, and so this is an inequality which is also quite useful in this story. And as you can imagine, it's not complicated to prove when you know it. And I'll just show you how it works. So the proof of this. So you have no choice. You want to estimate this quantity. So what you do is write it as it is, which is, so there will be always a sum of I and j in all these inequalities, but I forget the sum, and implicitly you sum up all the E and the I. So you depart from di di u 1/2. Oops, I have to do it better. So di u 1/2 squared, dg u 1/2 squared. Okay, so this is the power 4 of the gradient. So the only way you can go is to integrate by part one of them. So you decide over I. And so this is minus, so this is di multiplied by di. So if I integrate by part, I will get a u 1/2. And either I integrate by part this one and I will get di u 1/2. Dg u 1/2 squared, or I integrate the other one and I will get di u, and then I will get a 2 di j u dg u. Is this what I get? No, this is not what I got. Yes, that's the trick. The trick is not to do it like that. The trick is to keep it is to keep it di u 1/2 di of dg u 1/2 squared, not to perform the chain rule at this level. And the reason, don't forget that the target is to find u, and not u 1/2, to get this. And so this you can write it as minus 1/2. And this one, what did I do here? Yes, so this one, so this is very simple, but you have to not to forget not to do it. So this one is integral. This one is the first one is dii u 1/2. This one here you have a dg u 1/2. Because I can enter one of them in this, paying 1/2 like this. And here, I can also enter and call it u. So, diu, di, dg, u 1/2 squared. If everything is correct, I still have u power 2 in all these terms, which is the case. Okay, so we are now not far from the answer. So you integrate again by part, and you get 1/2 of, so this one, I don't like it because I like only derivative of u per 1/2. I like the second derivative of u. So I integrate by part, I get di u 1/2, dij u, dg u 1/2 plus diu, Laplace u, grad u squared, u 1/2 squared. Okay. And I forgot one term. So which one? Okay, and here I made a mistake. I forgot when I integrate by part, I have also plus, so what did I do? I integrate by part this one, di u 1/2, dg u, dij u 1/2. Okay, and let me check if I agree with myself. So this one is agree. There should be this one is fine, and no, I do not agree with myself. Di 1/2 d. So this one I got it. This one I got it. This one di u 1/2 dju dij is here, and this one you can integrate by part. And this one I claim it is diu. So why is it the dju? After integration, this is dju, dj of diu 1/2 squared. And this you need a 1/2. So this term, you write it like that, and now you are happy because by integration by part you get again the Laplace u and the grad u 1/2 as you like. So you achieve the goal, which is to get only second derivative of u, first derivative of u 1/2, and so you are at the end of the troubles, and And in principle, there are two terms which should arrange. So this one gives you minus 1/2 of this one after integration by part. So here, if you allow me to do it quickly, this one after integration by part, I can cancel it with 1/2 here. Okay? And so now you are done because you just use Cauchy-Schwarz. And by Cauchy-Schwarz, you control this by 1/2 of integral of grad u 1/2 fourth. This is this one and this one. An integral of d2ij u squared with a square root. But this is, when you integrate by part, of course, this is Laplace u squared, because then you can integrate by part again the square. And this one is 1/4 of integral of Laplace u squared, integral of grad u 1/2 fourth square root. Okay, so you get exactly that you control the power 4 square by the square root multiplied by this. And when you count the numbers, it's 1/4 plus 1/16. That's the reason why you have 9/16. I don't know if this number is sharp, by the way. This is what you get as this proof. So I don't know, so this is a very nice inequality, which is the one used by Brecht and Desjardins. This one, what we need for us, contains a p, so it's not exactly the same, but with playing with the weights, you get estimate of the same style. So all this you can do if you accept the initial data in L2. And then this estimate will be in L2 spacetime, in L4 spacetime, if you accept the initial data in L2, a gradient of the initial data in L2. So these are estimates which you can do, which are compatible with the right-hand side, and which gives a simpler proof than if you accept the stronger assumptions. Yes? No, I don't. Strictly positive, yes. If you depart positive, strictly positive, you are parabolic, so it will stay smooth. If you make a C infinity with compact support, then Baron-Blatt will come and you'll get a sharp front created automatically. In any case, when gamma tends to infinity, so if you want something uniform, it cannot be true. In the end, you have free boundaries. So whatever you do, gamma tending to infinity, any regularity will collapse. Any regularity which contradicts sharp fronts on the density. This doesn't contradict that the cell density can have a discontinuity. It just tells you that the pressure is smooth, but not that not that the density is true, is smooth. Okay? If it's a jump compatible with the if it's a jump compatible with this complementarity condition, yes. The jumps and the pressure can only be where Laplace P has a singularity. The jumps of n can only be where the Laplace P has a singularity. P has no jumps because it's, okay, we'll see that the P is smoother. So this tells you a lot of things. It doesn't tell you how the solution behaves. The real estimate which tells you how the solution behaves is the Aronson-Benillan estimate, which is much more subtle than the others, and it's much more subtle than just integration by parts with subtle weights. It's gives you inequalities which do not use any assumption of the initial data. So these are regularizing effects. So depart with initial data, which I said are in L1 and L infinity with this homeostatic pressure, nothing more. And what the Aronson-Benillan tells you, so when for the Proust medium equation, it tells you that the Laplace of the pressure, the Laplacian of the pressure, will automatically become bounded from below. And it's become controlled from below by minus 1 over gamma t, which means that at t equals 0 you need nothing. It's just an inequality which tells you that you don't need an assumption for the initial data. And it tells you when gamma is large, that the Laplace of the pressure will be positive. And if you add up the right-hand side, the inequality becomes this one. So you get still the regularizing effect at t equals 0, which tells you that immediately this quantity becomes bounded, and because P is bounded, Laplace P becomes bounded from below. But it's more than that. It tells you also that for large terms, you have an exponential decay due to this term. You don't have it here, it's not true here. Which also shows something interesting. It is that this term, G of P, is not only a right-hand side that is playing no role and it's coming like an additional burden. It interacts with gamma, which means the pressure law, to create something like this exponential decay. So the result is much more than just a right-hand side that is just added to the equation. It really interacts. There is an interaction between the two terms. And the proof of this inequality is still using the equation of the pressure. So I begin with the porous medium equation because there it is very simple. So you use the equation of the pressure, which is on the blackboard, and you compute. So you're interested, you know, of course, when you know the result, you know that the interesting quantity is the Laplacian of the pressure. So you define W equal Laplace P. And from this equation, you differentiate twice to compute the equation of the pressure. So if you differentiate, so if you differentiate once the equation on P, the first term will give you 2 grad P grad of dP dxi, let's say, if you differentiate xi, this term grad P squared, and on the other term will be giving you gamma dP over dxi Laplace P plus gamma P Laplace of dP dxi. So if you differentiate again this quantity to get the Laplace P, what you get here is firstly due to P, 2 grad P Laplace, graded of Laplace P, but then you have to eat this term also, and this will be giving you a term like that with a factor 2, by the way, which I forgot. Okay, so there is a factor 2 here coming from this term here. Okay, and then if you compute this term here, you get these 3 terms, 2 grad P Laplace When you differentiate here, you get this one, and when you differentiate here, you get this one, and when you differentiate here, you will get a Laplace p squared. So when you differentiate this one again, you get this W squared. And the important term is the W squared. All the other terms, so this one is positive, so it will make a it will make that W increases, and W large we don't care, we want to control from below. So this term is not bad. And the other terms are more or less linear terms, if you look at them in terms of W. So the only thing you keep on that is that that W is a super solution of this parabolic equation with a drift and a source term. And for parabolic equations, you have a comparison principle, and it turns out that -1 over gamma t is a solution of this. Because if you take -1 over gamma t, here you get 1 over gamma wt squared, which is exactly this gamma w squared. And this is 0, because it doesn't depend on x. So a super solution is larger than the solution, so you know that Laplace p, which is w, is larger than this. So you use this w squared, which is quite bad because it makes that the second derivative can blow up, but from below it helps to regularize the solution. And this is, of course, something you find in many examples of PDEs where you have singularities. You have always a side which is regularizing and a side which is destroying the regularity. So this tells you more or less what is the maximum regularity. The advantage is it is sharp. It tells you what is the maximum regularity you can expect. The second derivative from above, because of this term, will blow up. So you cannot think that the second derivative will be controlled from above. So this is what happens for the porous medium equation. If you do it for with the growth term, you can do it. Then what you want to control is this term, Laplace p plus g of p. And the reason you want to control this, it is the term which will converge to 0. When gamma is large. So you know that if you want to control something nicely, this term is a nice term that you should control. So you call it W, and now you compute dt. You compute okay, let me think. Yes, you control this. You write it like that, and you calculate the derivative of W. And if you compute the derivative of W, what you get out of it is still an equation, a linear elliptic equation LW in a strong form, so which has a maximum principle. You get this term gamma W squared, which is still there, and you have an extra term. And this extra term has the advantage that PG is always positive, G prime is negative, so this is positive, and so this term is, let's say, give you this rate of decay, because you see that this is a negative term, so this positive is negative term. So this is an absorption term, which in the long range, in the short range, this one is playing the important role and give you this. In the long range, this one is the important one and give you an exponential decay. And that is the way this Aronson-Bellon estimate can be extended to the term with a source term. Let me add a remark on that. So this is quite simple. This is a control just by regularizing effect, because you use the comparison principle. In many cases, you cannot do it like that. And especially for, I don't know of any system relevant from what we said yesterday for which this can work. you can not consider, if you put a nutrient, this will not work so well. I mean, this will not work like that. If you put a drift, it will not work. If you take a system of different types of cells, it will not work. So what we, and of course the estimate is very useful because it gives you the regularity. So the only way we could find to go around this is not to work in L infinity, but to work in L2. So this is an operator in strong form, but nevertheless, if you use it, you can take, you can consider a negative, again, you do it more or less like I did it before, you take the negative part of W, and you can get L2 estimates on the negative part of W. If you do that, you have to pay, because then you need an estimate, you need that the initial data is controlled in L2. I mean that the W initially is controlled in L2, which is a strong assumption. But if you do that, you get the regularizing, you get the same type of inequalities, but in L2. So you control the second derivative like that. In fact, you can control, by the way, the third power, not only the second power of W, you can control the third power of W by this variant in L2. So I will not do it. It's become a little bit tricky to do all the calculations. It's a little bit long, but so there are variants, and these variants are useful for other problems. So what are the conclusions of that in terms of what you really see now? So we have inequalities, we have theorems. What do you really see in practice? So the first theorem which I would like to point out is a theorem which follows from this Aronson-Bennion estimate, and which tells you the following. Imagine that initially your function n0 is the indicator of a function of a set omega 0, which is a set where p0 is strictly positive. Then, for all time, it remains true. I don't say that this is an open set. I don't know if p0 is continuous. I don't know what is this set. It's just a measurable set. And I claim that for all times, there is a measurable set, which is exactly the set where p of t is strictly positive almost everywhere, and that n is 1 on this set. So just nothing more than that. Okay, so this is the situation you see here in one dimension. Gamma very large. The solution is, okay, this is my computation, so they are not very accurate, but this is 1, this should be 1, and this is the free boundary, so you get the set 1 over omega t, and the pressure is exactly like this. Okay, so if initially you put an n0 which is 1 or 0, then the pressure is satisfying this, and you see that the pressure is either 0 or satisfies the Laplace equation. So the complementarity condition is satisfied. So P, Laplace P plus G of P, infinity, that's for the limit, is 0. But if initially you put an initial data with a tail, which is a green curve here, it's not always 1, you see that it's more tricky what happens. So the first thing which happens is that n, the green line, the density increases. When it reaches 1, you create the free boundary, the pressure is built up, the pressure pushes the cells on the right, and these cells which are on this mushy region, what I call the mushy region, where P is 0, so they don't move, there is no active motion, these cells are just pushed by the pressure, but there is no pressure. So this is growing exponentially, but the free boundary, which is an hyperbolic effect, is winning. And so what you observe is that this pressure builds up, pushes the cells which are developing by pressure, by passive motion, and then invades all the domain. Okay? So this is an example of what happens when n is not initially an indicator function. The blue is the pressure. Blue is the pressure, it's smooth. I mean, it is either 0, P equals 0, or Laplace P equals minus G, so it's concave. And this is the cell density N. So the cell density, which satisfies this transport equation. When the pressure is 0, so in this zone where the pressure is 0, what you get, this is 0, you get exponential growth. G of 0 is large. So when n is strictly less than 1, n power gamma and gamma equal infinity is 0. N power infinity is 0. So this is what happens here. In this zone, n is less than 1, pressure is 0. Okay? And because we are in the limit, gamma tends to infinity.
This is solve the limit equation, not solve the primary equation when n large. So this figure comes from the solve.
Yes, it comes from the limiting equation, but the limiting equation is the same. It's the same, except that in some, but this becomes wrong. This is, so this is, the second rule is that P 1 minus n infinity is 0. So either P equals 0 or n is less than 1. Either P equals 0 or n equals 1, which is what you see. Either P equals 0, which is fine here, or n equals 1. And here n is strictly less than 1, so the pressure is 0 until it builds up. It doesn't happen in practice. You cannot have both P equals 0 and n equals 1. This happens exactly at this point. At this point, you have P equals 0 and n equals 1. But this is a zero measure set. So this is, in fact, this is. If you put n equal to 2, it will decrease very quickly because if you take n equal to 2, the pressure will be very big very quickly, and this term will regularize. You have a regularizing effect immediately. I don't know if someone studied precisely this boundary layer. So if you find it complicated, there is even worse. So, in fact, what we know is lacking for the usual Elisho theory. After some time, in any case, all singularities will cancel, and will be in the situation where n is an indicator function. So after some time, we will always be in the situation where your cell density is like this, and the pressure will be like this. And this in dimension less than 3. Okay? But to arrive to that, you have to fight much more than what we have seen. You have to fight also this kind of situations where you have two islands of densities. So here you have a cell density which is 1. Here you have a cell density which is building up, creating a new island of pressure. And at some point, these two zones, these two tumors will join, and suddenly they create a single tumor. So until a certain time, you get two islands. You get something like that and something like that, with a cell density which is one here and one here. And exactly at the time where they join, you switch to that, which means that you have discontinuities in time which occur regularly because of this phenomena. So if you take an initial data which is even smooth, but with small ions, these small ions will build up, like the one on the right, will create a new free boundary which will propagate and will eat the other free boundaries to create bigger islands. And at the end, you will get a single big island altogether. So what we know that these things will occur, and after a certain time, they will disappear. So what do we know for the other models? So I told you other models are when you create nutrients. So for nutrients, we know the result. We know that everything is true. We can pass to the limit. We can get the complementary condition. We can get the free boundary problem. For that, you need variance of what I said. So you need the Aronson-Benedict estimate in L2, not in L infinity, in L2. And you need the estimate, which is here, the L4 estimate on the pressure, which follows from that. So these tools are enough to treat this case. It turns out that in medical science, it's important to take into account that cells are not only pushed by passive motion, they are also active. Some cells acquire phenotype which make them motile. And then they move actively. And this is the reason of metastasis. Metastasis occur because cells get moved by themselves and are not only pushed by the pressure. In that case, you should add in the equations, in the equation which is here, Laplacian. So you get this term. Okay? In that case, what I said is still true. You can prove the L-ratio limit, you can prove the complementarity relation. What you get is that the cell density now is smooth because you have diffusion. So in the limiting equation, the diffusion remains. So the cell density is smooth. It will reach 1 at some point because you have no choice. When P is strictly positive, you need that N equal 1. And though the pressure will be again, it satisfies this, so the pressure has still a corner, which is compatible with the Aronson-Benedict estimate, which tells you that the Laplace P is controlled only from below, so you have a second derivative which can be big, but not big. The second derivative, can be large, but not very small, but it's controlled from below. So this is still what you see here because this is still true. But the solution is smooth. So this is what you obtain for active motion. When you go to systems of cells, different types of cells, things are becoming much more tricky. And maybe I will not go further in this case. Existence and incompressible limit is proved, but not with this right-hand side, with what they call autophagy, which is moving effect on that. This is by Liu and Xu. Mats Jacob has preprint this recently, where he has another approach, which is called the Lagrangian solutions, and he can prove the Aronson-Benedict estimate for this equation, and then he handles this equation here. And now Emmy David has also an existence, an incompressible limit by the weak method I explained yesterday. So this is a situation for this system which is a little bit more tricky. So this is also an Aronson-Benilian estimate in L2, not in L infinity. Of phenomena? Yes. Yes, this is what he proved, Jacob proved, is that the solution is non-mixing. Non-mixing means that when you have, in this zone, you have one cell or another type of cells, but you don't mix the type of cells. They separate. So now the picture is a little bit more complicated. You have a zone where the cells 1 are represented, the zone where you have the cell 2 represented. So this should not be in blue. So the pressure will be like that. And the cell 2 will be like that. Okay? So this is the picture you get. So the sum of the cells is 1, and 1 plus N2 is 1. The pressure is everywhere, but the cells do not want to mix. And they move, this one moves like that. Here. And this one moves like that. No, this one is, I think it's fixed, by the way. I think it is fixed. I don't know. I don't know. This is, this is a good question. I think it's, I think, okay, but okay, we can see it because the equation is something like that. So the interface moves with the gradient of the pressure. So no, this moves. If I know, yes, because each equation satisfies an equation like that. You just simply say Ni, Ni, Ni. Okay, so the velocity of at a certain point, the velocity is the gradient of the pressure. So this one will move in that case because the pressure is negative. It should move in the sense like that. It's positive, so it should move like that. In my drawing, it should move on the left. Okay? So this what should be true. So this is for this one. Then you can also do, so there are experiments, by the way, in biomechanics, where they show that the Darcy's law is not always enough. And though you can have viscous effects, which mean that you need to add the viscosity of the flow. And then you replace the Darcy law by this equation. So you add viscosity for the velocity. So you are closer to Navier-Stokes equation. So if you want, these are the Navier-Stokes equations in which you neglect acceleration. Okay, so this is something you need to show. Okay, and to explain you the physics of this, so when you do Darcy law, you say, okay, there are fibers and my cells attach to the fibers, so there are friction against the fibers. If you put viscosity, it means that the cells have friction in between themselves. And so if they have the same velocity, the friction is 0. But if there is a difference of velocity, then there is friction. And difference of the velocity, the second is a Laplacian. Okay? So this is what means this term. It's just a friction between cells themselves. And there are experiments where they show this effect can occur, so you get it. Then it's one of these contradictions where you think that adding viscosity will simplify the game and will get new estimates, it will be easier. It's not true. Adding viscosity here makes a nightmare because now this equation becomes just a transport equation. And all what I said completely collapse. You are in the world of hyperbolic equations, of shock waves and oscillations. You are no longer in the parabolic world. And so this becomes completely different. And you have to use different tools based on entropies and things like that to study this phenomena. So we could prove it without proof of the results, but many questions are still open about the viscosity elastic models. And what you observe now is that the pressure has discontinuities. And this is typically, if you ask to a mechanician what is the effect of viscosity, he will immediately tell you it is to make that the pressure becomes singular. So this is a contradiction. You put viscosity, and the result is you get singularities. So this is, again, like in the Turing instability, one of these counterintuitive effects. So the V term here is the friction. There's a friction on the boundary, on the fibers, and the other is the friction between cells. So what we said so far was nu equals 0. We are neglecting this. You have a jump here which is proportional to the viscosity. Someone asked me the question of different motilities. So now you arrive with really something which is completely open in terms of mathematics, is what happens if you put motilities which are not the same in the two types of cells. So what you observe in some experiments are these kind of fingers of dendrites, which can go very, very far away and detach. And if you want to reproduce them, this Safman-Taylor instability type is able to represent this kind of, but it's very complicated computationally to get them, but you get these fingers created. And this is what Alexander Lortz and Tommaso Lorenzi did some years ago. So all these things are relevant for biology, and are of level of difficulties which are from easy to impossible. So you have a full range of problems if you are interested in working in this. Many questions are open. So there are a lot, there is a beautiful community working about that with new ideas. But there are different tools to work with this, as I mentioned earlier. It's not only I presented the PDE point of view with functional analysis, but again you have a viscosity point of view, you have a obstacle problem points of view. So it's a problem, it's a subject where you have many open questions, either from mathematical ingredients, either from the modeling. So, okay, welcome. I stop here, and we'll continue in half an hour.